Good morning. Myself Dr. SaradaJayan. I will be giving a presentation on generalized Gaussian quadrature rules over n-dimensional ball. The outline of my speech will be as follows. Initially, I will be talking about the mathematical preliminaries, about numerical integration, generalized Gaussian quadrature, derivation of the quadrature rules over a disk, a sphere over an n-dimensional ball. Then I will be giving few numerical results, and then finally we will be discussing about the summary and conclusions. So initially I will just start with why actually we need numerical integration. So there are many times where the integrand is not known to us, only the value at some points is given, like the data is given to us. So in such a case, numerical integration of that is not possible, and many a times what happens that the function does not have an antiderivative. For example, e of x square is a function which doesn't have an antiderivative with respect to x. And also in other case, it happens that some functions, even though e of y is a very simple function, it cannot be integrated over some domains. Now if you try to integrate this e of y over this integration domain, we are not able to find the antiderivative. So we cannot integrate that function over this domain. So basically that is the reason why we need numerical integration. So numerical integration is basically an approximation of an integral to finite summation values, where you will be calculating some points, xi points corresponding to some weights will be given to you, and the function value is evaluated at those points, multiplied with the function with the weight. The summation of all those points are taken to finally get the value for the integral. So if the dimension of the integration is 1, for one case of one-dimensional integration, we say it is a quadrature formula, and if the dimension of integration is more than 1, we call it as a cubature formula. The error of the integration, we call it as I of f minus. This is the value obtained by the quadrature formula. If this error is minimal, the integration formula is considered to be very good. Now coming to what is meant by generalized Gaussian quadrature rules. So the same integration formula, we call it as a generalized quadrature rule with respect to a set of 2n functions, phi 1, phi 2, etc., phi 2n. If this quadrature rule exactly gives the integral value for those set of functions. So in such a case, we say it is a generalized Gaussian quadrature formula with respect to those set of 2n functions. And the generalized Gaussian quadrature nodes and weights, these are called as the nodes. The xi values and wi values are called as the weights. The generalized Gaussian quadrature nodes and weights for different basis functions in the interval 0 to 1 is given in this particular reference paper by a person called as Ma. So starting with the numerical integration method over a two-dimensional ball. A two-dimensional ball is just a circular disc. A disc is called as a two-dimensional ball. So derivation of this numerical integration method. So three different methods I will be explaining here for integration over this particular domain. So the method 1 explains, it's a method where we are directly applying the formula. This formula is a direct formula which is given in references 9 and 10. We will be applying this particular method in order to find the quadrature points. These are the quadrature points xm and ym, and cm. This is the weight wi which we mentioned in the previous slide. So to evaluate this is a direct formula given. So for this particular region, we will be able to get xm, ym and cm in this particular manner. In method 2, we apply a different kind of transformation. We apply initially a polar transformation, and after applying a polar transformation, after converting it to a rectangle, we will be applying a linear transformation. So initially a polar transformation is applied. This is a polar transformation we will be applying. X is r cos theta, y is r sin theta. So that the domain of integration will be from the circular disc, the domain of integration will be transformed to a rectangle in the r theta plane. So in the rectangle, having the length 2 pi and breadth as a. So this particular integration gets transformed to this, where the Jacobian is r in this particular case. The Jacobian of the polar transformation is r. And after that, this integration domain, which is a rectangle now, is converted to a square. So in the xi1, xi2 plane, so the standard square with the endpoints are 0, 0, 1, 0, 1, 1 and 0, 1. We are converting it into square because the generalized Gaussian quadrature rules are given over the 0, 1 square in the MA paper. So this transformation to a square from the rectangle is using this particular linear transformation. R is a xi1, theta is 2 pi xi2, which gives us a Jacobian of 2 pi into a. So that the integration formula now becomes integral 0 to 1, 0 to 1 with this as your function, and the Jacobian term which you get will be this d xi2, d xi1. So here we combine this whole thing as xm, this whole thing as ym, and the remaining terms as cm, which is the weight. Thus we will be getting the quadrature points xm, ym in this way and cm the weight using this particular formula. And we have the third method, where we apply the same method as method 2, but we take different node points along the xi1 and xi2 direction. This is to ensure the uniform distribution of the points. So here the same transformation is used, only thing is the number of points we take for xi1 and number of points we take for the value xi2 is different in this particular case. We can compare all these three methods using the distribution of the points for each case. So when you apply method 1 with n equal to 5, so these are the set of points. So method 1 uses a linear transformation. So due to that you can see that the distribution of the points is in a linear fashion. And method 2, so all the points are distributed linearly. You can see that all are parallel to the y-axis. The method 2 gives a distribution of points. Here polar transformation is used, that means a transformation which corresponds to a circular domain. So you can see that all the points are distributed in a circular fashion in order to apply the quadrature rules. And the third method gives a much better way, that is the points are distributed. So here only 5 points are taken along one direction and along the other direction 10 points are taken. So a uniform distribution of all the points are seen in this method 3. So if you compare the results of integration for all these three methods, so we have taken up 5 different type of functions. A linear function x plus y, a trigonometric function sin of x plus y, and a polynomial function x power 4 plus y cube, and then we have taken a function, a fractional function, and then a big polynomial function. All these functions are being taken from papers in literature. It can be seen that the method 1, the accuracy of method 1 is quite less compared to the accuracy of method 2. So here we have written the errors which is obtained, that is the exact solution with the solution that you are getting. When you compare the errors, you can see that it is approximately same as the exact solution which you get. The error which you are getting is quite less in method 2, and when you compare with method 3, we can see that the accuracy is almost same here, but in brackets what is written is the number of function evaluations that we need to do. So in method 2, the function evaluations is quite less compared to method 1. For example, for the first function, only with 15 nodal points we are getting an accuracy of up to 15 decimal places. In this method, so basically method 3 gives better accuracy with minimum function evaluations. So we prefer method 3 compared to method 1 and 2. Next we will be deriving the same thing for a 3-dimensional ball which we call is a sphere. So this is a particular sphere. Here we apply the same concept as in 2D. In 2D we were transforming it to a rectangle, then to a 0, 1 square. In 3D we will be transforming the sphere to a cuboid and then to a 0, 1 cube. So the transformation goes like this. This is the complete derivation. These are the transformations used, the polar transformations from the spherical transformation from the spherical coordinates to the cuboid, and then the linear transformation is applied. So finally we will be able to get the nodes as xm, ym and zm and the weight, which is Cm, is given in this particular manner. So the distribution of the points when you apply that particular formula is this. And we have taken few functions for which we have done the evaluation. The exact solution for integration over the unit sphere, which is x square plus y square plus z square less than or equal to 1, is this. And the error obtained by applying the method. The third method is applied over here for 3 dimension. We are getting an accuracy of almost up to 13 decimal places. The same thing derived for an n-dimensional case. This is an n-dimensional ball, an ND ball. So for the ND ball, after applying the polar transformation, this becomes the integral value, and then it is reduced to an ND cube. So when it is reduced to an ND cube, this becomes the integration formula, and the xm value is this, ym and zm. The function values for all these are given here. The Jacobian of the transformation is given, both the Jacobians in this particular one. So the derivation completely goes like this. This is a complete transformation. And this is the second transformation which we apply, the linear transformation, which transforms the n-dimensional cuboid to an n-dimensional 0, 1 cube. And finally, this is the formula. The first Jacobian comes here, and the second, after the second introduction of the second transformation, the second Jacobian comes. So finally, this weight function into the Jacobian is taken as Cm. This, and then the xm, x1m, x2m, xnm terms are calculated according to as shown in the previous slide. So finally, we will get the formula for n-dimensional in this particular manner. The integral is summation Cm f of x1m, x2m, etc. xnm. All these set of points x1m, x2m, x3m, etc. xnm, when you calculate finally, will give you the node points which will be used for integration, and for the corresponding points the weight value is given by the Cm. So Cm is given here, 2 into a power n pi xi1 i1 raised to n minus 1 sin n raised to n minus 2 times pi xi2 i2 sin raised to n minus 3 times pi xi3 i3 etc. sin pi xi n minus 1 I n minus 1 times all the weights w1 i1, w2 i2 etc. w1 i2. Now all these points in these equations are the node points between 0 and 1, and they are the corresponding weights for one dimension. The results over n ball, we have taken up few functions from this function from a standard paper. So it gives the integration of this, because we have only the exact solution for this particular function. So when you compare the result with for dimensions up to 5, we have calculated over the two-dimensional ball, that is disc, sphere, and we have also calculated for the 4D ball and 5D ball. So the results of integration are as follows. So here also we can see that the error which we are getting is very, very small. Now coming to the summary and conclusions, using a combination of few transformations, integration formula are derived to integrate functions over n-dimensional balls. So transformations are more important in this particular paper. It is because of the transformations that we are getting a very good accuracy over here. Then all these derivations are based on different type of variable transformations, and here we have seen that an n-dimensional ball is transformed to a 0, 1 n cube. The integration rules which are derived here are very simple, general, simple as well as direct. So you can apply this for an ND ball, so a 4D ball, 5D ball or a 6D ball as well. And it is generally we have given for integrating any function f of x. So if the function can be of different types, still you can apply the same formula. It is very simple because once the formula is known to you, you just have to substitute the formula. So it is that way very direct also. Then in order to apply this formula and to get the integration nodes and finally the integral value, you can use any programming language like C or Java or any mathematical software also. can be used to evaluate the integration results. Most of the numerical results obtained using these new quadrature rules are exact for at least 10. So in most of the examples which I have shown here, the minimum accuracy is 30 decimal places. But still for some complicated functions which has singularities, we have seen that the accuracy is reduced to 10, but still we are getting 10 significance digits accuracy. The distribution of the derived quadrature points for many regions is plotted in the paper as well as shown in the slide. The proposed integration methods work well for all types of integrand functions. So even if it's an oscillating function, or you have the integrand to be a function with endpoint singularity, which is having a singularity along the border of the disk or the sphere, even for such functions, this integration method gives a very good result. These are the following references behind the paper. Thank you, and I take this opportunity to welcome all of you to Amrita Vishwa Vidyapeetham. That is our campus in Bangalore. Here we have a lot of research in many fields like numerical integration, finite element methods, fluid dynamics. There are many people working in graph theory too, so whoever is interested to apply for PhD, welcome to our campus. Thank you.